Okay, let's solve the following problem. We have four charges, and we would like to see how much work we actually need to do in order to assemble the charges in the way that they are going to be represented. We have three different uh, positive charges placed in different positions and one negatively charged particle. So we have this kind of setup. And what we want to do is to find out how much energy we actually need to expend in order to get the charges to these positions. I have here these four beads, and I'm going to be representing the red and pink as positive and the blue one as the negative. So let's start by assembling this in stages. If I want to look at the amount of work needed to bring this positive charge from very far away and put it in this place, I will find that I don't actually need to do any work if there is no other force acting on it, if there are no charges close by. And therefore, the work done to bring this over here is going to be equal to 0. I'm going to call this now Q1, Q2, Q3, Q4. And in this problem, all the charges have the same magnitude, but they might differ in the sign. So the work needed in order to bring this one over here is equal to 0. So W1 is equal to 0. That's the work needed to bring this one from infinity and put it here. Now, if I fix this in place, and I want to bring another charge and put it over here, then clearly there's going to be a repulsion between the two, and I will have to be doing some work in order to overcome the electrostatic force. Okay, so if I do that, then I'm going to be doing this kind of thing. If I leave this charge here, while this is being fixed, then this is going to experience a force of repulsion in this direction, and it's going to fly away. And so in bringing this from infinity and putting it over here, I'm actually doing work. So how much work is actually needed to do this? Now remember that the potential energy that's stored in this system, in a system of 2-point charges, is going to be the product between the charge that I'm bringing in and the potential that's going to be coming from this other one. Now we said in class that the potential for a point charge is equal to kq divided by r. Okay, now this actually is also the potential difference between the position of that point charge and a point very far away or a point at infinity. So in reality, you can either use this or this to stand for the same thing by assuming that the reference point is at infinity, because this thing is going to be equal to 0. And the work done in order to achieve this is going to be equal to the new charge, the charge that I'm bringing in from infinity. In this case, that would be 2. And the potential that is coming from the first one. And I'm going to call this W2. Okay, so let's multiply these, and we get K Q1 Q2 divided by R. Okay, now in this problem we're assuming that all four charges are going to be on a square that has length L. So this distance in this case, R12, is equal to L. The two charges are positive, their magnitude is the same, and so we can simplify this as follows: K Q squared divided by L. Okay, now let's see what happens if we want to bring in a second charge. So in this case we have Q1, Q2, and Q3. All of them are at the corners of the same square, so R12 is equal to L, R23 is also equal to L. Now this also is not going to be interacting with Q2, it's also going to be interacting with Q1. And so let's get back to the setup that we had. We have this now and this. Both of them are fixed in space, and these are our sources. What I'm doing now is I'm bringing from very far away this new charge and trying to put it here. It's experiencing repulsion from these two other charges, and as a result of that, I'm actually also expending work or expending energy in order to do this. So the work done to bring 3 is going to be equal to the charge itself multiplied by the potential I'm going to be getting from 1 plus the potential I'm getting from 2. Q3 times the potential from 1 is going to be K Q1 divided by 1 R13 plus the potential coming from the other one, it's going to be K Q2 divided by R23. All of them are positive, so I can extract the Q's outside. I'm going to get an overall factor of Q squared, and I already have the K, so it's going to be K Q squared. And as for the length, well, R13 is equal to this thing, which is actually the hypotenuse in this triangle. So I have this, and R23 is equal to this length, which is just L. Okay. Now, what happens if we bring in the the fourth charge and put it over here? Let's do that now. So again, Q1, Q2, Q3, and now Q4 is negative. The lengths are the same, the L's, and now I'm interested in R14, R24, and R34. Now the work done to bring 4 in is different. So I'm going to be fixing these now in place, so I'm assuming that they don't move as a result of the forces they're experiencing. They're glued in space. And I'm going to be bringing this in. Now what happens if I put it here? If I put it here, then it's going to be feeling a force of attraction from all of them. And so in reality, what I'm going to be getting is actually an excess of energy. It's going to move by itself towards them. It doesn't have to be moving in this trajectory. We'd have to actually position it properly to do that. But it's going to be attracted here. And so we're actually gaining energy. That energy is going to be kinetic. So instead of putting into the system some energy, we're actually obtaining some energy. And so as far as the system is concerned, we're actually getting some negative work being, as far as we're concerned, we're actually doing some negative work. And that actually is going to come automatically from including the sign of this charge. Okay, so Q4 times the voltage or the potential difference that's between the position of V1 and infinity, the same thing for the second one and the third one. And as you can easily see, based on the lengths that we had from the previous parts, we can write this directly. Q4, the potential due to the first one at the position of Q4 is going to be KQ1 divided by R14. From the second one, it's going to be KQ2 divided by R24. And from the last one, it's going to be KQ3 divided by R34. Okay? Now, Q4 and all the others have the same magnitude, but Q4 is negative. So we can extract a factor of minus Q squared from all these terms, and we get an overall factor of this, minus KQ squared. And what remains is 1 over each one of the lengths. Now, R14 is equal to L. R24 is the hypotenuse of this triangle, which is the square root of 2 times L, plus R34, which is 1 over L. Okay, so now we have all expressions, and we can collect all of them. So the net work, oh, this doesn't show here. Let me move it a little bit. The net work in this case is going to be equal to W1 plus W2, W3 plus W4. That's the work needed in order to bring all these charges and putting them in these positions. Okay, so we have seen that the work done to bring in the first charge was equal to 0. There was nothing next to it. Then for the second charge, we have found this to be KQ squared over L. For the third one, it was K, oops, let's get rid of this here, KQ squared 1 over L. And now for the fourth one, we add this term, and now notice what's happening. Let's add all of these together. We have 1 over L here and another 1 over L. And we have the same thing over here, but with a negative. So this means that this and this cancel out this and this. And likewise, this is the negative of this, so this goes away with this. And we actually end up with 0 multiplying the KQ squared over L, which is just 0. So this means that we ended up with a net work equal to 0 needed to assemble this. And this resulted from the fact that we had to expend energy, positive work, in order to get these in place. But once we inserted the negative one, we actually gained some energy by way of kinetic energy form.